Okay, so in this video, I'm going to solve the problem on the adiabatic batch reactor that we derived in class. And this time I'm going to use the online PolymathPlus server, which is free. A limited version of this is free to anyone who has an account. And one of the stipulations to the free account is that you can only have, I think it's 10 explicit equations. So I'm going to enter in equations in an attempt to reduce the number of equations so that we can use this free server. Okay, so if you recall, this is a adiabatic batch reactor, a liquid phase reaction that's irreversible. A plus B goes to C. I'm going to start out by putting in the mole balance and the energy balance. So the mole balance is going to be dx dt is equal to minus Ra times V divided by Na naught. I'm going to save some equations, and I'm just going to say that Na naught is equal to Ca naught times V. Now I'm going to do my energy balance. So that's going to be dt dt. This is an adiabatic reaction, so I only worry about the heat generated from the reaction. That's going to be negative heat of reaction times negative Ra times the volume. That's going to be divided by the sum of the product of the number of moles of each species times the heat capacity of each species. You can do some algebra and prove that denominator term for this reaction is equal to Ca naught times V times CPC. A special case where that just happens to be true. Okay, so now I'm going to enter in my initial and final conditions. The original value of x is equal to 0. The original value of t is equal to 300. The original value of time t is equal to 0. And then the way we tell the solver our final t is using an f in the argument. I'm going to integrate this for 300 seconds because I've already done it before and I know that that's the right answer. If you didn't know the right answer, then give a guess value and you can adjust by solving the problem. All right, so this is what I now need. I need expressions for all of the things in here, so I'm going to start adding those in. So I'll start with Ra. I don't want to enter in a negative, putting a negative sign here. Math software doesn't really know how to handle that, so instead I'm going to define positive Ra is equal to, and that's going to be negative K times Ca naught squared times 1 minus x squared. K, I'm going to use the Arrhenius equation, so that's going to change as a function of temperature. I know from the problem statement that it's equal to 0.01 per molar per second at 300 K. So I'll use the Arrhenius equation to take care of that. The Arrhenius equation is going to be the activation energy divided by R, which I'm just going to enter those values in to save some equations here, but normally I would type that all out explicitly. All right, so that's my K. Ca naught I know from the problem statement is 0.1 molar. What else do I need? Volume is going to be equal to 10 liters. The heat of reaction, we solved for that. It's going to be negative 6 kilocalories per mole. And the last thing I need is CPC, which is equal to 30 calories per mole Kelvin, or 0.030 kilocalories per mole Kelvin. So I'm wanting to keep consistent units here, so I'm writing time units in seconds. I'm writing concentration units in molar, which is moles per liter, which means I'm writing volumes in liters. I'm writing moles in moles rather than kilomoles. And I'm writing energy units in kilocalories and temperatures in Kelvin. Okay, so I think that should be good unless I miss something. I'm going to click solve here. Oh yeah, and so that works. I get a solution. So this is a plot here. This is putting x and t on the same graph. Of course, x only goes from 0 to 1, so it's way down here and we can't even see it. We can see our t graph pretty well. Starts out at 300, which is the initial temperature, and it goes up to about 500. In fact, we can look at the maximum values, 498.3. If I wanted to plot x separately, I could do that. I'm not going to do that for this particular problem. In fact, there's a second way that we could do that. Maybe I'll go over that in just a second. Anyway, so this gives us one thing that we're looking for. Now let's consider the situation where we wanted to get the plot of x explicitly. Since this is an adiabatic reaction, we can do that. To do that, we can comment out this differential equation. And instead write an explicit equation for T. So T, we could say, because this is an adiabatic reaction, the temperature is only defined by the conversion. If this system had a heat exchanger, then the heat exchanger would help define. And then because of that, the way the heat exchanger is configured, which depends on the reactor, so we wouldn't be able to use an explicit equation. We'd have to use a differential equation. When we have an adiabatic reaction, though, the only thing that affects the temperature is the reaction itself. So we can write a function for the temperature in terms of conversion. And so that's going to be equal to this T equals T naught, which in our case is 300, times negative heat of reaction times X divided by, and then we'll have again our heat capacity term on the bottom. In our case, we're just going to put our CPC term. So now we should be able to just solve this. Now we get our plot of x because we are no longer looking at, we're no longer have a differential in terms of t. So because of that, Polymath doesn't plot that. So we can just get our plot of x versus t. And then we can look up our final temperature here, which we find to be approximately the same answer, this 498.3. And this is using this explicit function for T for temperature, which we can use because this is an adiabatic reactor.